Section 4.2, Linear Approximations and Differentials. We're going to start off by looking at an example that illustrates how we can use tangent lines to approximate the value of a function. We'll start by finding the equation of a tangent line of f of x equals the square root of x at the point 4, 2. Since we're trying to find the equation of a tangent line, the first thing we need to do is find the derivative of our function. Treating our square root of x as x to the 1/2, applying the power rule, we get that f prime is 1/2 x to the negative 1/2. Since we need to find the slope of our tangent line, meaning we have to take 4 and plug it into our derivative, we're going to rewrite our derivative so it no longer has negative exponents or exponents that are fractions. Since our exponent is negative, we can make it positive by bringing it to the denominator. And x to the 1/2 is the same as the square root of x. So f prime of x is equal to 1/2 root x. Now that we have f prime, we can find the slope of our tangent line at 4 by plugging 4 into our derivative. And we get that our slope f prime of 4 will be 1/4. Now we can find the equation of our tangent line. We'll start off with our point slope form, y minus 2 equals 1/4 times x minus 4. Then we'll manipulate it into slope-intercept form. And we get y equals 1/4 x plus 1 as the equation of our tangent line. Now we're going to evaluate our function, f of x, and our tangent line for various values of x. Starting off with 3, if we plug 3 into f of x and approximate, rounding to 6 decimal points, we get that f of 3 is approximately 1.732051. If we plug 3 into our tangent line, whether we use Desmos or calculate by hand, we get approximately 1.75. Notice how close 1.732051 and 1.75 are. When we plug 3.5 into our function and our tangent line, 1.870829 for f of 3.5, while our tangent line at 3.5 is 1.875. These two values at x equals 3.5 we can see are even closer together than our function value and our tangent line was at x equals 3. Now we'll plug in 3.9 and we get 1.974842 for our function value at 3.9 and 1.975 for the value of our tangent line at 3.9. And we can see that our values are getting even closer still. Our function at 3.99 will be 1.997498, while our tangent line at 3.99 is 1.9975. If we plug 4 both into our function and our tangent line equation, we see both would be exactly 2. It does make sense that f of 4 would be 2 since the point 42 does lie on the graph of our square root function. Also, it does make sense that our tangent line would be 2 at x equals 4 since the equation of our line came from the point slope form knowing that the point 42 was already on it. But observe as we plug in values from 3, 3.5, 3.9 to 3.99, all the way to 4, notice that the value of our tangent line is closer and closer to the value of our function. If we continue to plug in values such as 4.01, 4.1, 4.5, and 5 into both our function and our tangent line, we see as we get farther from 4, the values of our tangent line are starting to get farther and farther away from our function values. What we can take away from this is that for x values that are around 4, our function and our tangent line are approximately the same value. As we get closer to 4, the closer our function and tangent line will be. But the farther we get from 4, the more the tangent line deviates from our function. This is not a coincidence, and this is one of the important characteristics of tangent lines. With the last example in mind, now we'll talk about linear approximations. We'll let f of x be a function that's differentiable at x equals a. We'll call the linear function L of x, which equals f of a plus f prime of a times x minus a, the linear approximation of f at a. One thing to note, all L of x is a tangent line of f of x at x equals a. It's just written in a slightly modified point slope form where we have f of a on the right-hand side as opposed to being subtracted from L of x on the left-hand side. The reason why we're calling the tangent line a linear approximation is, as we've demonstrated in the previous example, when x is very close to a, we have that L of x is approximately equal to the actual value of our function at x, which would be f of x. Below, we see a graph of f of x equals 1/x and the tangent line of f of x at the point 2, 1/2. Notice how in this window, it appears that the tangent line and our curve are overlapping. However, if we zoom in to where x equals 2.1, notice that the curve and the tangent line do have some space in between them. Because tangent lines are very close to the curve for values of x that are close to a, we can use tangent lines as a way to approximate our function. And this can be very helpful when trying to evaluate functions at rather difficult inputs. Next, we're going to let f of x equal the cube root of x, and we're going to use linear approximation to approximate the cube root of 127. In order to make our linear approximation, we'll start by finding the equation of our tangent line of f of x equals the cube root of x at some convenient point. Since we know we need to find a tangent line, we need to find a derivative of our f of x. The cube root of x is the same as x to the 1/3. So f prime of x would be 1/3 x to the negative 2/3. Since I'm going to have to plug in a value into our derivative, we should rewrite it so there's no negative exponents and no rational exponents. We can make the exponent positive by bringing the x to the 2/3 to the denominator. Then we can rewrite the x to the 2/3 as the cube root of x squared. First, let's note that the cube root of 127 is f of 127. So in order to make my tangent line I should pick a point with an x value that is really close to 127, but it's very easy for me to take the cube root of. Since we know that 125 is a perfect cube, and that the cube root of 125 is exactly 5, then we should use 125 as the x-coordinate of the point to find our tangent line. Now, from our decision, we already know that f of 125, which is the cube root of 125, is 5. So our tangent line that we're going to try to make for our linear approximation is going to pass through the point 125, 5. For the slope of our tangent line, we're going to plug the 125 into our derivative. Since 125 squared is going to be a really large number, we can switch the position of the cube root and the square. And we can take the cube root first and then square it. The cube root of 125 is 5, squared is 25, and 25 times 3 is 75. So our slope will be 175. So our linear approximation L of x using the slightly modified point slope form where we add over the y1 will be 5, which is our y1, plus 1 over 75, our slope, times x minus 125. Now we could simplify this, but since we're plugging a value in, we'll just keep it as is. Because we're trying to approximate the cube root of 127, the cube root of 127, thanks to our linear approximation, is approximately equal to L of 127, which will equal 5 plus 1 over 75 times 127 minus 125, which will equal 377 over 75. So what we have is the cube root of 127 is approximately equal to 377 over 75. We're going to let f of x equal the natural log of x, and we're going to use linear approximation to approximate the natural log of 1.01. Just like before, I should start by finding the derivative of the natural log of x. Using our basic rules, f prime of x is 1 over x. Now I need to determine a convenient point to try to make my tangent line for the linear approximation. Since we're trying to approximate the natural log of 1.01, I do want to pick a value very close to 1.01 that is easy enough for me to approximate the natural log. The easiest inputs to evaluate the natural logs for are ones that are powers of e. Well, the only power of e that's close to 1.01 would be 1, which we know is e to the 0th power. So the natural log of 1 would be 0. So our f of 1 would be 0, which is easy enough for us to plug in, which means we want the tangent line for the linear approximation to pass through the point 1, 0. For the slope of our tangent line, we'll plug 1 into our derivative. We got 1 over 1, which is just 1. Now we can form our linear approximation, our tangent line, which we'll call L of x. Using the modified point slope form, our L of x would equal 0 plus 1 times x minus 1, which simplifies nicely to x minus 1. So our natural log of 1.01 is approximately equal to L of 1.01, which is 0.01. So natural log of 1.01 is approximately 0.01. Next, we're going to turn our attention to differentials. We're going to talk about the applications of differentials first. In future sections, we are going to see differentials quite a bit when we discuss integration. We're going to let y equal f of x be a function. Delta x and delta y are going to represent the change in x and y respectively. In general, that little triangle symbol is referred to as the Greek letter delta, the capitalized version. Oftentimes in mathematics and science, delta is used to represent the change in a specific variable. So if x1 f of x1 and x2 f of x2 are 2 points on the graph of f, then delta x would be x2 minus x1, and delta y would be f of x2 minus f of x1. Delta y would be the numerator of the slope of our secant line connecting the 2 points, while delta x would be the denominator of the slope connecting the 2 points. Oftentimes, we're going to want to approximate the delta y. We're going to let dx equal delta x represent a very small change in x. dy equal f prime of x dx. Now, dy and dx are referred to as differentials. Now, what's really important is if dx is really small, then thanks to what we've discussed with linear approximation, the delta y would be approximately equal to delta x. And we can see this relationship in the figure here to the right. We have L of x, which is the tangent line or linear approximation of f of x at the point A, f of a. If we move over delta x units to the right of a, notice the 2 points of f of a plus delta x and L of a plus delta x. F of a plus delta x would be the actual value of our function at a plus delta x, while L of a plus delta x would be the approximate value using our tangent line to approximate. dy would represent the vertical distance we would have to travel to go from f of a to L of a plus delta x, while delta y would be the vertical distance we would travel to go from f of a to f of a plus delta x. Notice how close dy and delta y are. As we make delta x smaller and smaller, the difference between the dy and delta y will also get smaller and smaller, which is why we can use dy to approximate delta y. One thing to note is if we do divide over the dx, we have that dy over dx equals f prime of x. The relationship dy equals f prime of x dx is not true because of the dy over dx and f prime of x both being used to represent derivatives. The specific dy over dx notation was invented to help us remember the dy equals f prime of x dx relationship. The Leibniz notation was designed to help us remember relationships with derivatives by making those relationships look more algebraic. So just be a little careful about why this relationship of dy equals f prime of x dx is true. The relationship was first established, then the notation was invented. Next, we're going to let y equal 3 sine x. We're going to find the differential dy when x equals 0 and dx equals 0.01. Recall from the previous slide, the differential dy will equal our derivative of our function, which here would be 3 cosine x times the differential dx. From there, we'll plug in our values for x and dx, and we get 3 times cosine of 0 times 0.01. Cosine of 0 is 1, and 3 times 1 times 0.01 is 0.03. What this tells us is that from x equals 0, if we increase our x value by 0.01, our function value will increase by approximately 0.03. Next, we're going to let y equal x to the fourth, and we're going to find our differential dy when x equals 2 and dx equals 0.21. So our differential dy will equal the derivative of our function, which is 4x cubed plus 2, times our differential dx. Now we can plug in our values. So our dy so far would equal the quantity 4 times 2 cubed plus 2 times 0.21. 2 cubed is 8, times 4 is 32. Plus 2 is 34, and 34 times 0.21 is 7.14. So what this would tell us is when x equals 2, if we increase x by 0.21, our function value will increase by approximately 7.14. Next, we're going to use differentials to estimate the amount of paint in cubic centimeters needed to apply a coat of paint that is 0.01 centimeters thick to a ball with a diameter of 2 meters. Since we are applying a coat of paint to a ball, that is going to cause a change in the volume of that ball. So the amount of paint we would use, being measured in cubic centimeters, would be the change in volume, which we can approximate using the differential dV. Now, how would we figure out dV? Recall that for a sphere, the volume could be calculated using the formula V equals 4/3 pi r cubed. If we take the derivative with respect to r, we get 4 pi r squared. So dV will equal 4 pi r squared dr. Now we need to identify what r and dr are in order to figure out our dV. Since we're told how thick the paint coat will be, that thickness is going to represent the change in the radius of our sphere. So dr will be equal to 0.01. As for the radius, we are told that the diameter is 2 meters. But this is where we have to be very careful with units. Our dr is currently in centimeters, and we want our dV to be in cubic centimeters. Now, since our diameter is 2 meters and diameter is twice the radius, then our radius is 1 meter. But in order to calculate our dV, we do need the units of dr and r to be the same. Since I want my units in cubic centimeters, let's convert the 1 meter to centimeters. Recall that 1 meter is equal to 100 centimeters. Now that I have my units matching, we can plug in our r and our dr into our dV formula. When we work out the arithmetic, we get that dV would be 4 pi, which would be approximately 12.57 cubic centimeters since our radius and our dr were in centimeters. So we will need approximately 12.57 cubic centimeters of paint in order to coat the ball with a layer of paint that is 0.01 centimeters thick.